Hello everyone, this is Wang from the Google Speech team. Today I'm going to talk about the speaker diarization system we developed at Google. This talk also corresponds to a paper we published at ICASSP 2018 titled Speaker Diarization with LSTM. So first, let me introduce the speaker diarization problem itself. By definition, speaker diarization is the process of partitioning an input audio stream into homogeneous segments according to the speaker identity. It answers the question, who spoke when? For example, in this figure, we want to know how many speakers are there, when did each speaker start speaking, and when did this speaker stop speaking. So why do we need speaker diarization? There are quite a lot of applications. For example, for medical record speech data, after we have transcribed the speech, we want to know which part of the speech was from the doctor and which part was from the patient. After we have the doctor-patient separation, we can build more structured knowledge from these medical records. Also, with diarization, we can automatically generate structured notes from meetings. We can use diarization to help improve source separation. We can also use diarization to help with call center data analysis. And the hero application of diarization is that it can help improve speech recognition word error rate. Here's an example. With the first pass ASR, we may get transcripts like, I would like to sort of by needle interrupt. But with diarization, we know that this non-utterance actually contains two speakers, and the speaker boundary is between the word to and the word sort. Then we run a second pass ASR on the two speakers separately and get transcript, I would like to for speaker 1, and sorry, but I need to interrupt for speaker 2, which makes much more sense. The first pass ASR produced the wrong transcript because the language model would highly discourage the 2-gram of the word sorry after the word to, and the diarization result helps to improve that unnecessary constraint. So we talked about what diarization is. Then let's talk about what diarization is not. First, diarization is not source separation. This is because in diarization, we usually assume there is no overlapped speech. If there is, we usually first remove it when we evaluate. However, people are starting to solve the diarization problem jointly with the source separation problem nowadays, which is a much more challenging task. Also, diarization is not equivalent to speaker change detection, although they are closely related to each other. In diarization, we care about speakers that have previously appeared in the utterance. For example, in the figure, every time we see a new speaker, we want to give it a speaker label, and for the red speaker, it appeared twice, and we need to give them the same label. However, in speaker change detection, there are no such labels. We only care about when a speaker change happened. Whether it's a new speaker or a previous speaker, we don't care. Diarization is also not equivalent to speaker recognition. Again, they are closely related. First, in diarization, we care about timestamps of each speaker, and we need accurate segmentation. Second, in diarization, there's no enrollment process. We don't register any speaker's voice before we run diarization. Speakers are discovered dynamically. Also, while in speaker recognition, we can either use short keywords like OK Google or use text-independent speech. But speaker diarization always handles text-independent utterances that are usually very long. Okay, that's for the introduction. In part 2, I want to talk about some background and give a system overview. Before talking about diarization at Google, I need to talk about speaker recognition at Google. For example, on Android, we have two applications of speaker recognition. The first one is called From Any Screen. No matter what app you are using, News, Maps, or Home Screen, you can use the keyword OK Google to wake the assistant. The second one is Voice Unlock. When your phone is locked, you can use the keyword OK Google to unlock it, without having to type the password. On Google Home, the application is known as Voice Match. For example, when you ask personalized questions like, "Okay Google, what's on my calendar?" the assistant will respond with a personalized answer for events on your calendar. But if you have other family members registered as well, when he or she asks the same question, "What's on my calendar?" the assistant will respond with events on his or her calendar instead of yours. And to use these features on Android or Google Home, the user needs to enroll his voice by speaking "Okay Google" 2 times and "Hey Google" 2 times. Then an averaged embedding vector of his voice will be stored on the device. Okay, with a basic understanding of Google's speaker recognition technique, let's take a look at the anatomy of a speaker diarization system. First of all, there is a voice active detector, or VAD, that detects the speech part from the audio and removes noise and other non-speech parts. Then, we need to extract segments from the speech, such that most segments contain only a single speaker. Next, we need to extract embeddings from each segment, and this part is based on Google's speaker recognition technique, which I just introduced in the previous slides. After we have the embeddings, we cluster them to determine the number of speakers and each speaker's timestamps. Some people use a resegmentation to further improve the diarization results. Our system haven't done that yet. And here is a diagram of our system. After the voice activity detection, we extract fixed-length sliding windows from the audio and run our LSTM network to produce D vectors for each sliding window. Then for each segment, we aggregate the D vectors that belong to this segment to produce the segment-wise embeddings. Finally, we cluster these segment-wise embeddings to produce the final diarization results. In our system, we can see that there are two parts that are critically important: the speaker embedding and the clustering. So let's talk about the speaker embedding first. Speaker embedding is the technique to extract fixed dimension vectors from audio that can discriminate different speakers. For example, utterances of the same speaker should have similar embeddings, and utterances of different speakers should have embeddings that are distinct from each other. Here is a brief history of several most representative speaker embedding techniques. There are, of course, much more techniques than the ones in this diagram. These are just the ones that I am most familiar with. Okay, in 2011, the A-vector approach was proposed, and since then, most speaker recognition and speaker diarization techniques are based on A-vectors. Then in 2015, Google published a paper about FaceNet, which used the triplet nodes to learn neural network embeddings for faces. Since then, lots of work started to use triplet nodes to compute speaker embeddings as well. As long as the speaker embeddings are extracted using neural networks, people call them D vectors. The letter D is for deep. Then in 2016, the end-to-end speaker recognition nodes was proposed, and in 2017, we proposed the generalized end-to-end nodes. Here is a diagram for the D vector system. Once we have a fixed-length segment of audio, we feed it into a neural network, which can be either feed for all the DNN or LSTM. In our case, it's LSTM, and we take the last layer, last frame output as the embedding, called the D vector. There are different methods to train D vectors. For example, in triplet nodes, in every step, we look at the three utterances: an anchor utterance, a positive utterance from the same speaker as the anchor, and a negative utterance from a different speaker. The noise is simply the difference between the two distances, such that the positive utterance is close to the anchor in the embedding space, and the negative utterance is far away from the anchor. This is a simple loss, and it correctly models the embedding space. However, the disadvantage is that it does not simulate the runtime enrollment behavior. So let's recall what happens in the runtime application. During enrollment, we collect multiple enrollment utterances from user and average the embeddings. And in the verification time, we compute the cosine similarity between the embedding of the verification utterance and the averaged embedding of the enrollment utterances to make our verification decision. The triplet noise didn't consider the enrollment process of a speaker recognition system. And this is why in 2016, the end-to-end noise was proposed, which simulates the runtime behavior of speaker verification during the model training. In each training tuple, n plus 1 utterances are used, where n is the number of enrollment utterances, and this is exactly the number of utterances involved in a verification decision. However, this approach still has one disadvantage. Most training tuples are going to be too easy, which makes the training very inefficient. That's why in 2017, we proposed the generalized end-to-end noise. In this approach, we train our model on batches, and in each batch, for each embedding, we only look at its distance to the true speaker centroid and the distance to the closest false speaker centroid. This makes sure that in every training step, for each embedding, we always only look at the most difficult negative pair. It's like the max margin principle in support vector machines, and you may call this closest false speaker as the support speaker. Generalized end-to-end noise is much more efficient than other noise functions, and for our diarization system, our speaker embeddings are trained with this method. So we have talked about speaker embeddings. Next, I would like to talk about clustering algorithms. In general, there are two types of clustering algorithms, online clustering and offline clustering. For online clustering, once we receive an embedding, we immediately assign a speaker label to this embedding. We cannot look at future embeddings. This is very useful for real-time applications, but the accuracy is usually not very good. For offline clustering, we first wait until we have all embeddings of the entire utterance. Then we run the clustering algorithm and assign speaker labels to these embeddings at the same time. Offline clustering will have much more latency and usually will have much better results than online clustering. For offline clustering, we can also perform additional post-processing, such as gap filling, short segment filtering, and resegmentation. We have developed two online clustering algorithms for our diarization system, the naive online clustering algorithm and the links online clustering algorithm. The first one, naive clustering, simply applies a fixed threshold on cosine similarities. It basically considers diarization as a dynamic and continuous speaker verification problem. Links clustering is much more complicated. It's an anisotropic, probabilistic, and generative method. It was originally developed for phase clustering. If you are interested in the details, you should read this paper authored by Philip. For offline clustering, we first tried k-means. For k-means, we use the k-means ++ approach for initialization and use the elbow rule to determine the number of clusters. These are both standard practices for k-means. However, we realized that using k-means for speaker diarization is very problematic, especially for non-Gaussian data, imbalanced clusters, gender, age, and racial effects, and for overlapping speech. As we know, speech data are often non-Gaussian. Here is an example of non-Gaussian data. Of course, for speaker embeddings, the distribution is unlikely to be like this. Here I'm just talking about the disadvantages of k-means in general, so using this extreme example. If we want to model the distribution with two Gaussians, very likely we'll get something like this, which is very incorrect. And the k-means represent clusters by hyperspheres, which are even simpler than Gaussians. Here is an example of imbalanced clusters. In speaker diarization, we see this when one person talks more often than the other. If we model the clusters by Gaussians, we may get something like this. Here is an example of the gender effect. There are 3 speakers, 1 female speaker and 2 male speakers. The 2 male speakers are relatively closer to each other, while the female is significantly further to them. If we run k-means, very likely we get a total of 2 speakers instead of 3. The 2 male speakers are very likely to be considered as a single speaker since they are close to each other compared with the female speaker. Here's an example of overlapping speech. The 2 embeddings in the middle contain overlapped speech from both speakers. Because the 2 embeddings in the middle collected the 2 speakers, k-means will very likely consider there is only one speaker, only one cluster in total. Because of the disadvantages of k-means, we decided to use spectral clustering. Spectral clustering can be viewed as a graph cut, and it overcomes all the above-mentioned issues of k-means. The basic idea is that we first compute an affinity matrix of the embeddings. Then we use the spectrum based on the eigenvalues of this matrix to perform a dimensionality reduction of the embeddings. Then we run a k-means on the projected lower dimensional embeddings. So for spectral clustering, the first step is to construct the affinity matrix using cosine similarities between embeddings. Then we apply a sequence of refinement operations on the affinity matrix. And I want to mention that these refinement operations are the key to the success of our algorithm. First, we apply a Gaussian blur to the matrix. This is to smooth the data and reduce the effect of outliers. Then we apply a threshold to each row of the matrix. This will zero out affinities between different speakers. A symmetrization operation follows to restore matrix symmetry after the thresholding. A diffusion operation is used to sharpen the boundaries of distinct speakers. Finally, we apply a row-wise max normalization to avoid some undesired scale effects. Here is a diagram of our refinement operations. As we can see, the thresholding is the most important operation here. If you want to know more details about these operations, especially the motivations, you should read our paper. During these refinement operations, we introduced the 2 parameters that should be tuned on a depth dataset, the Gaussian blur curl sigma and the row-wise threshold. The row-wise threshold is a percentile p, and we use soft thresholding instead of hard thresholding to avoid having too many zeros in the affinity matrix, which may crash the final k-means algorithm. To find the number of clusters, we use the eigengap. The optimal number of clusters should maximize the gap of eigenvalues. In this example figure, the gap has max value when k is 8, so 8 clusters is optimal in this case. So let's see how spectral clustering overcomes the failure cases of k-means. Here's an example of non-Gaussian data. Spectral clustering should be able to find an optimal graph cut based on the local pairwise distances. This is an optimal graph cut when the clusters are imbalanced. And here's the optimal graph cut of gender effects. This is the optimal graph cut when 2 clusters are collected by embeddings from overlapping speech. Okay, we've talked about speaker embedding and the clustering algorithms. Now let's talk about metrics and datasets for diarization. The biggest difference between the evaluation of diarization and the evaluation of other systems is that the matrix must be permutation invariant. Let's consider this example. The sequence of speaker labels in ground truth is A, B, B, C, A, and the sequence of speaker labels in the hypothesis is C, A, B, C. These 2 sequences are actually equivalent. We just need to map speaker A to C, B to A, and C to B. The solution to this permutation invariance is that before computing errors, we first need to find an optimal speaker mapping between the ground truth and the hypothesis. Finding this mapping is just a standard assignment problem and can be solved with the Hungarian algorithm. So let's look at the different components of the error. Here is an example. First, there can be miss and false alarm. These two types of error are usually introduced by the voice activity detector and the segmentation. Then there is overlapped speech. Most people exclude this part from the final errors. Finally, there's confusion errors, which means one speaker was mistakenly labeled as another speaker. This error is mostly related to the diarization algorithm itself, and in most papers, people only report this number. Diarization error rate, or DER, is the ultimate metrics for a diarization system. It includes all types of errors, and by definition, this value can be even larger than 1. However, it's important to note that in literature, most people report only the confusion part and refer to it as the diarization error rate. To evaluate our system, we use the PyAlert matrix library. We highly recommend this library for diarization evaluation to our colleagues. This is a modern library. It's been actively maintained, and bug fixes are usually pretty quick. The code itself is easy to read and understand, and there are very detailed documentation. Most importantly, as far as we know, this is the only diarization evaluation library that has good test coverage. We use the 3 public datasets to evaluate our diarization system. The first one is the Disk 8 of year 2000 list speaker recognition evaluation dataset. This dataset is usually referred to as core home by most papers. It contains 500 short utterances, and each utterance has about 2 to 7 speakers. These utterances are from 6 languages. And there is this core home American English dataset used by a few papers. Especially, some papers use the 2-speaker-only subset for evaluation, and this subset is known as CH109. Finally, there is this year 2003 list rich transcription dataset. We use the telephone speech part of this dataset to compare different algorithms of our own system. There are several conventions and common practices when people evaluate their diarization results. First, people usually merge multi-channel audio to mono-channel before the diarization. Second, people usually exclude overlapped speech from the evaluation. For the RT03 dataset, there are some files called the unpartitioned evaluation map files. We only evaluate on the segments defined by these files. For SRE 2000 and Core Home American English, people usually tolerate boundaries offset errors less than 250 milliseconds. This tolerance value is known as the corner value in the PyAlert matrix library. Now we've talked about the metrics and the datasets. It's time to show the performance of our system. To train our models, we use anonymized voice searches, which contain 36 million utterances from 18,000 speakers. It's important to note that our training data is completely out-of-domain data compared with the evaluation datasets. So if we compare the performance of our system with other systems, we are actually in a very unfavorable position. It's much more difficult for us since we are generalizing across domains from voice searches to telephone speech. Our voice activity detector is a super simple model. It has just 2 full variance Gaussians, one for speech and one for non-speech. Our I-vector model is trained with PLP features. The GMM background model has 512 Gaussians. The total variability matrix has 100 eigenvectors. The final I-vector is 50-dimensional. Our D-vector model is a 3-layer LSTM. Each layer has 768 nodes with a 256-dimensional projection. There is a final linear layer of 256 dimensions. So here is our results on the 2 English-only datasets. Some quick conclusions. Offline clustering has significantly better performance than online clustering. Links online clustering is better than naive online clustering, and spectral clustering is better than k-means. Also, D-vectors are much better than I-vectors. Actually, although I vectors are not as good as D vectors, they should not be this bad. Our I vectors are really bad here, mostly because they are trained with out-of-domain data, and I vectors do not generalize very well across domains. Another disclaimer is that since our clustering algorithms have some parameters, and the voice activity detector also has a threshold, so we always separate a dev set from the eval set for parameter tuning. Okay, this is our d-vector plus spectral clustering method versus other people's work on the list SRE 2000 core home dataset. We get a confusion of 12.0 before any resegmentation, which is the state-of-the-art performance. However, we need to admit that the comparisons are not apple to apple, which is an unfortunate fact in the Diarization community. There are several reasons for this. First, people use different voice activity detectors, and they are not publicly available, so the false alarm and miss will be very different. Second, people use different evaluation softwares. Some of those softwares are really old and difficult to use. Again, we highly recommend to use PyAdult Metrics, which is a very nice and modern library. Third, people use different datasets for training and parameter tuning. And finally, some people have a final variational Bayesian resegmentation step after the clustering, which is the VB value in the table. Here is our performance on this CH109 subset of core home American English. We tried to align our evaluation with this paper and got a confusion of 5.97 compared with their 7.84. For this evaluation, the number of clusters is fixed to be 2. So the conclusions of this talk. At Google, we built a state-of-the-art speaker diarization system. The system is based on our text-independent speaker verification model, which is trained with generalized end-to-end loss. The model has 3 LSTM layers, and it runs on sliding windows. The system is also based on spectral clustering. We use the eigengap to find the number of clusters, and we use a sequence of refinement operations on the affiliate matrix. Okay, I have talked about what we have already built at Google. Now let me talk about what we are building for the future. The holy grail of speaker diarization is end-to-end diarization. This means there is only one single neural network model to replace the complicated system. There will no longer be separate modules for speaker embeddings, segmentation, clustering, and other things like VAD or resegmentation. Only one neural network that does everything. This would make the model development significantly easier and faster. To do this, the most important part is to design a loss function that's directly based on diarization error rate. This means that this loss function needs to be a permutation invariant loss. Some acknowledgements. We want to thank Dr. Avi Braden from CNRS. He is continuously supporting and improving the PyAdult Metrics library. He replies to our questions very quickly. Also, we want to thank Dr. Gregory Stell and Professor Pietro Lafacci for sharing the ground truth nibbles with us and helping us understand the evaluation datasets and protocols. We want to thank Yash Sheth and Richard Rose for the helpful discussions. Let me know if you have any questions.